This video is all about position and displacement vectors and how we can use the principles of vector math that we already know to apply it to the context of position and displacement. So just a couple reminders before we get started, just to make sure we all have the same vocabulary. I just want to go over just a few things. So the first one is what a coordinate system is. Remember, a coordinate system is a set of unit vectors that define our space. We've been working with a Cartesian coordinate system. So your x hat, y hat, and z hat unit vectors define your space. They each describe a different dimension of space. The origin of our coordinate system, we haven't really used this very much at all. The origin is a location. It's a specific location at the intersection of our axes of our system. So when you draw the x-axis, the y-axis, and the z-axis, they intersect at some location, and that's called the origin. So if you were defining points in your system, the origin has the coordinates 0, 0, 0. And it's really important to understand what an origin is, because when we're talking about position vectors, all of them are measured relative to the origin. A norm is the length of a vector or the magnitude of a vector. And the norm is always a positive number. Remember that the norm describes the length of an arrow vector, and length has to be positive. You can't have a negative length. Direction of a vector describes how the vector points. So when you draw your arrows, make sure that they have like a tip, that they have a direction to them. Don't just draw lines, draw arrows. And the last thing I want to mention is the phrase component form. That means that I want you to express your vector as a combination or the addition of its vector components within our coordinate system. So remember that a component can either be a scalar component or a vector component, and you can express your vector as vector components along the directions within your coordinate system. So like some number times x hat plus some number times y hat plus some number times z hat. That would be your vector expressed in component form. All right, so now that we have all those vocabulary terms, now we can describe position vectors. So the position vector has a symbol, and that is a lowercase r with the little vector sign on top of it to show that you are describing a vector. So the r symbol means position. A position vector will have units of meters or really any unit of length. So if you see feet, inches, centimeters, those are acceptable units. The standard SI unit is the meter though. And a position vector, I would describe it as a vector that starts on the origin and ends at a location in space that you're trying to describe the position of. So you must define an origin for your coordinate system in order to define a position. You have to establish your coordinate system and where 0, 0, 0 is so that you can draw these vectors relative to that origin. You must do that once, and then whatever problem you're working on, everything in that problem gets defined relative to that origin. So for example, if you've ever looked at a map, you'll see a lot of lines on the map, lines of longitude and latitude. And there actually is an origin for a map, the intersection of your lines of longitude and latitude. The 0, 0 mark is right here somewhere in the Atlantic Ocean. And that's the origin of every map. We need some kind of common reference point so that we can describe locations. So if I wanted to describe the location of Jacksonville, Florida, I could use this map, and that would be the position vector that I would draw. The tail of the position vector is at the origin, and the tip of it is at the location I'm describing. So that length of the vector describes the distance, the straight line distance from the origin to that location in space. So just to be really, really careful here, I want to reiterate that you must establish the origin of your coordinate system before you can ever describe a position, because a position is relative to something else. It's relative to that origin. So you can't draw a vector, you can't draw a position vector unless you have established the origin of your coordinate system. And once you've chosen that origin, it has to be the same origin for everything in your problem. And the position vector will describe how far away the location is from that origin. And this is a really unique property of position vectors. No other vector depends on the origin. We don't have to always establish a coordinate system or an origin, an axes, or anything like that, unless you're describing position vectors. You must do it for a position vector. So to give you an example here, let's say I have like a dog in a tree. I could choose my origin to be right here. Here's the origin of my system. Let's say x hat going to the right is positive, y hat going up is positive. So if I wanted to draw the position vector for the dog, it starts at the origin and it ends at the location of the dog. So I could call this R and I'll give it the subscript dog to show you that this is the position vector for the dog. If I wanted to give you a position vector for the tree, it would look something like that. So this is R and the little subscript says tree to show you that this is the thing that I'm describing with this position vector. If instead I wanted to choose a different coordinate system, let's say maybe you're doing this and you chose a different coordinate system, well, then your position vectors are going to look different. Let's say that you chose your origin to be down here. So this is the intersection of my axes, so that is the origin. You still like having your x's going to the right and y's going up. But this time when you draw your position vectors, they're going to look very different. So this is the position vector for the dog for your coordinate system. And this is the position vector of the tree for your coordinate system. It's defined relative to your choice of origin. So you must establish it, draw it, tell people where it is, and then everything is measured with respect to that as far as position vectors are concerned. So now let's talk about displacement. Displacement describes a change in position. When you see the symbol delta, that triangle, the triangle is the Greek letter delta. And it literally means a change. So if you see delta R, that means a change in R or a change in position. We give it the name displacement. So displacement is a change in position. It will also have units of meters or whatever units are of your position vectors. And it literally means a change in position. So this displacement vector will start at some initial position and it will end at some final position. So the displacement vector is not defined relative to the origin. It is defined relative to some initial position and some final position. You can use this equation here to describe displacement. It's R final minus R initial, where those are vectors. So it's vector subtraction. So again, if I had my map here and here's my origin down here, let's say there's my initial position. We are sitting here in Jacksonville, Florida. So there's our initial position vectors. Imagine we're going to get on a plane and we are going to fly to China. So there's our final position vector. Now we are in China. To describe our displacement, we're going to draw a vector whose tail is at the initial position and whose tip is at the final position. So there's our displacement vector right there to describe this change in position from going from Jacksonville to somewhere in China. So again, there's the equation. You should write this down, have this in your notes, that displacement delta R is R final minus R initial. That's what those little subscripts mean, final and initial. You could rewrite that equation as R final plus negative R initial. And so if you do this, now you can use vector addition, the steps of graphical vector addition, to draw this arrow. So to remind you about the steps of vector addition, you can do this graphically by drawing the arrows. First, of course, establish your coordinate system. Then draw your initial and final position vectors. You needed that origin in order to establish the initial and the final position vectors. And in order to do vector addition, we really want R final and negative R initial. So you're going to draw negative R initial. Once you know R initial, now you can do negative R initial. It's just if you flip the direction, flip that vector 180 degrees. And now you follow the steps of vector addition. So you place the two vectors tip to tail. So place negative Ri tip to tail with RF, and then you draw the resultant. You draw this new vector that starts at the tail of negative Ri and it goes to the tip of RF. These are just basic steps of vector addition that you already know. So I did not teach you anything new here. This is just basic vector addition. So let's do a little example here. Here's my dog in my tree again. This time I'm going to draw my origin of my coordinate system over here. So I'm just saying this is my origin right here. So let's follow those steps. I'm going to draw both of my R final and my R initial. So the dog near the rock is the initial position, and the tree is the final position. So there's my RI, that describes the initial position of the dog. There's RF, that's the final position of the dog. Now that I've established those two vectors, now I want to find negative RI. Negative RI is just RI flipped around. So there's negative RI. And I'm adding, remember that displacement is RF plus negative RI. That's why I found negative RI, because I'm adding those two things together. So I place those two vectors tip to tail. They're already tip to tail for me by definition here. Okay, and now I draw my resultant vector. It starts at the tail of my first one and goes to the tip of my last one. So there is delta R. That's my displacement. It literally describes how the dog changed. He was initially at the rock and now he's at the tree. So that's the displacement vector to describe the change in position of that dog. I have a question for you. Do you think that that choice of coordinate system determined the displacement vector? We've already established that the position vectors definitely are determined by our choice of coordinate system. But what about the displacement vectors? Let's try this problem again. But I'm going to define a new origin of my coordinate system. So I'm just going to remind you, this is our original, this is the one that we just did. That was the displacement vector of the dog in that previous example. What if we define a new coordinate system where the origin is up here somewhere? Do you think we're going to get a different displacement vector? Well, let's go through those steps again. There's RI and RF. So those are the position vectors of the initial position of the dog and the final position of the dog. He starts at the rock and he goes to the tree. I'm going to find negative RI. So I flip that vector around. I place them tip to tail. They're already done. It's already done for me. It automatically becomes tip to tail. And now I'm going to draw that displacement vector, or the resultant of this vector addition. And so that displacement vector starts at the tail of the first vector and goes to the tip of the last vector. And what do you know? We get the exact same displacement. So displacement vectors do not depend on our choice of origin. It's only position vectors that depend on our choice of origin. The dog moving from the rock to the tree was a physically observable event. Like, it doesn't matter how we describe that event. That is exactly what happened. He started here and he went there. And so whether we choose to put our origin up here or down there, it doesn't matter. The dog went from here and went to there. So that displacement vector is always going to be the same, regardless of our choice of origin. The last thing I want to mention is, really honestly, while graphical vector addition is good to visualize what's going on, the more accurate way of dealing and calculating displacement vectors really has to be the component form method. Put your vectors into component form and then just subtract them. So if you're using this, this equation up here, if you put your final position vector in component form, you put your initial position vector in component form, you can just subtract them and do basic math. So this is the method you're probably going to use more than anything, but the graphical method is good to visualize. So let's say I have this example here. Here's RF and RI, and I want to find delta R. So literally delta R, remember, is RF minus RI. So that's going to be negative 5 meters x hat minus 2 meters y hat minus 4 meters z hat. And then minus RI. So RI is negative 9 meters x hat plus 2 meters y hat minus 4 meters z hat. Make sure that you are subtracting all of RI. So be real careful with your vector subtraction. But when I've written everything in component form, it's really just basic math. This is just following arithmetic and algebra. So I'm going to group the x hat terms together. I have negative 5 meters x hat minus negative 9 meters x hat. So that gives me positive 4 meters x hat. Now I have negative 2 meters y hat minus 2 meters y hat. That gives me negative 4 meters y hat. And then the last one, I have negative 4 meters z hat minus negative 4 meters z hat. That goes to 0 meters z hat. So my final answer, 4 meters x hat minus 4 meters y hat. And that's how you would find the displacement vector, just using the component form. It might require you to put vectors into component form, but I know you guys are capable of that because we've done it before. And you can refresh your memory by going back to those pages and going through the steps of how to put a vector into component form.